Okay, so we're on chapter 16. This is 16.1. It's on vector fields. And you've spent all this time learning how to do computations throughout the calculus series. And now we start really showing how the calculations can be applied in just really interesting sort of physics situations. We have to learn how to do new types of integrals called line integrals, and then later surface integrals. You've now integrated through solids of any shape, but you haven't integrated along curves before. You've integrated lengths of curves, which is sort of like the line integral, but what if the curve had mass? What if you needed to know its center of mass? So that's a line integral. Also, when you do work along a curve in a field that's variable, then the work is a lot more complicated than the work problems you've done in the past. And so work is also a line integral because you're summing something up along a curve. I don't know, they should call it a curve integral, I guess. But then after that, you need to learn how to do a surface integral. A surface integral is just like a line integral, but it's going to be, line integral is a single integral, where a surface integral is a double integral. You're summing over a two-dimensional surface that lives in three-dimensional space. And so surfaces can have mass. So they would have, if they have mass, then they have centers of mass. And but more importantly, surfaces are important because of flux in physics. So we'll do physical properties of surfaces, but we'll also learn how to compute flux, which is a surface integral. And then doing mass and moments and centers of mass, that's a surface integral as well, if it's over a surface. Okay, but all of the interesting things that we study, primarily work. There's an integral called a circulation integral, and then flux. Those are integrals over objects that live in fields. So a field is a new type of function that you've seen vector fields. Primarily the gradient of a scalar function has a vector output and a vector input, because it inputs a position vector and it outputs a vector field. Okay, so that's just sort of a summary of what we do in this chapter. Super interesting chapter. There aren't any really new computations other than the line integrals and the surface integrals, but in the end, line integrals are just single integrals and surface integrals are just double integrals, and they're related to surface and surface area, and line integrals are related to arc length. So nothing fancy there, but again, in the end, our goal is to integrate through fields. So we have to introduce vector fields now. So a vector field has a position vector input. And some field output. Okay, so I'll just say a field vector. Output.
So I believe your screen's frozen.
My screen's frozen. Dang it. That makes me very angry. Still frozen. Ugh. How about that? Hey. Okay, so yeah, vector field has position vector input and a field vector output. So, I mean, it's pretty simple. If you think about gravity, your position determines the gravitational vector. If you are on the surface of the Earth, like where you're sitting right now, then the gravity points toward the center of the Earth. But if you're 1,000 miles out in space, the gravity still points to the center of the Earth, but it's a lot weaker. And depending on your position, the direction to the center of the Earth is probably a different direction from what it is for you right now. So this is a varying field that depends on your position. So the most important fields that we study are gravity, I'll say gravitational, electric fields, oops, magnetic fields. There are other fields in physics that I know next to nothing about. Like I know there's a field for the Higgs boson particle, and I believe it is the Higgs field that gives objects mass. And I don't know anything about the Higgs field, but I do know that gravitational and electric fields have inverse square properties. So we'll talk especially about inverse square vector fields. And magnetic fields are like that, but they're complicated because they have poles. Magnetic fields are crazy. Okay, I just want to go ahead and just give you notation. Maybe a two-dimensional version, you'd have like an F of X, Y. Notice I put the barb. We always use capital F for field. So that's a two-dimensional input. And we put a barb over the F because it's outputting a vector. So you'll have like a P of XY and maybe a Q of XY. Okay. And those will always be the components names that I use. Maybe sometimes I'll do X of XY. No, that's not good. I can't do that. I have to do P and Q. Okay, and then of course in 3-dimension, and that's a vector output. So in 3-dimension, it'll be the same, but obviously there's going to be an F of XYZ as a position vector, outputting a vector PQR, P of XYZ, Q of XYZ, and R of XYZ. Okay, so this is nasty business. And if you think about derivatives and stuff, there's 3 functions. They'll each have 3 partial derivatives. That's 9 derivatives altogether. And when we talk about the total derivative, like the gradient, remember, was a vector of partial derivatives. And we call it sometimes the total derivative. Then the analogy here to the gradient being the total derivative is going to be a matrix with 3 rows and 3 columns. There are 3 functions, P, Q, and R, each with 3 partial derivatives. Altogether 9 partial derivatives. The total derivative is a matrix for a vector field. Let's do a quick example. We'll do a simple one. So here I'm going to do F of XY is a vector, negative y over 2, comma, x over 2. This is one of my favorites because it's just so innocent looking, but it's sort of gnarly when you graph it. So how do you graph a vector field? Well, with a whole bunch of vectors that are positioned at the position vector. So, and I hate to do this to you, but I don't know what else to do. So here we go. So just real quickly, it's easy to see that the position, the input vector 0, 0 has an output of 0, 0. Okay. And then let's do 1, 1. The output here, it reverses the coordinates, changes the sign of the y, and divides by 2. So you're going to get a negative a half, positive a half here. Okay. Then 0, 1. You reverse the coordinates, divide by 2, and change the sign of the y coordinates. So it's going to be negative a half, 0. Okay. And then negative 1, 1. Switch the coordinates, change the y, so they're going to both be negative. You're going to get a negative a half, negative a half. Okay. Then a negative 1, 0. Again, switch the coordinates. First one's going to be a 0. You divide by 2, you get a 0. The other one's going to be a negative a half. Okay. Where am I? How about negative 1, negative 1? So you get to switch the coordinates so the y becomes the x and then becomes positive because you're changing the sign, so you get a half. And the x becomes a y, that's a negative a half. Okay. How about 0, negative 1? I don't think I've done that. These are just points very close to the origin, and there's a lot of them. Okay, switch the coordinates. The y becomes the x and it changes sign. You get a positive a half. The x becomes y, stays 0. Okay. How about a 1, negative 1? This is going to output to a half. Okay. How about a 1, 0? This is going to switch to 0, a half. Okay, so again, when you graph this, it's going to be sort of a lattice of points that get associated to vectors. And it's just a lot of info. And probably you don't ever really want to graph one of these by hand, I think. But we'll just do one. And again, we start with sort of a lattice of points. And I'm going to allow myself to go outward a little bit from these points that I'm drawing first. But all I did was use these as my input points. This is not very symmetric. Somehow I feel like I should have done better. Just a little better. Not great. Okay, and then one way to think of this is, well, first of all, 0, 0 maps to 0, 0. So I'm just going to draw a dot there. Okay. But then the 1, 1 goes left and up. A half, a half. So watch what I draw at 1, 1. Just like this. So it goes back a half and up a half. Okay. At 0, 1, it goes negative a half, 0. So this is 0, 1 going back a half and 0 on y. Okay. At negative 1, 1, it goes left a half and down a half like this. Okay. You see I've done 4 problems. 1, 2, 3, 4. At negative 1, 0, it goes nowhere to the left and down a half like this. Let's check. At negative 1, it goes positive a half and down a half. So this is going to go to the right and then down a half. Maybe to there. Okay, little check mark there. At 0, -1, it's going to go a half 0. That's easy. Just to the right then. So that's fine. At 1, -1, it does a half. Okay, so that's to the right a half and up a half to the here. And then at 1, 0, it's going to go 0 a half, so it just goes up a half there. Okay, so this is interesting. It's sort of a swirling thing. I think just for the heck of it, let's do a couple more, just so we see what the pattern looks like. Okay, so let's do a 2, let's do a 2, 2. Okay, and I think you know that the coordinates switch and it's half of what it was before. So you're going to get the y coordinate just goes to the x and half of it. Change the sign and then half of it. The x coordinate goes to the y and half of that. So 2, 2 becomes -1, 1. And I think I want to draw that here. So I'm going to go out to this point here. And then it goes left 1 and up 1. Like that, maybe? Okay. And then maybe what I'll do is I'll just draw, I think I know, I get the pattern here. So I'm going to continue my lattice a little bit and add some more points here. And these are, I'm just going to kind of infer what the vectors would be. I probably won't do a great job, but I'm still sort of interested in trying to represent what's going on. Oh God, that's horrible. I'm ashamed. Ugh. Okay. And yeah, doesn't matter. I'm plowing ahead. Sorry about that. Oh, I just know I got confused on that one. I think I put in more points than I meant to. I'm not going to do that last one there because it's throwing me off. Okay, so this guy here should have gone there. And this guy here goes there. And this guy here is going to go to there. Yeah, that's better. So I don't want to fill in all these points because it just muddles the picture, I think. And I think I have another mistake over here, but I'll fix it like this. See, this is what happens when you just sort of guess. Yeah, that's good. That's what I want to see there. Pretty good. I'm happy. Yeah, it's good. It's solid. All right. Now, so this is sort of like a whirlpool. Okay, and I want to go ahead and show you how to do vector fields in Maple. Okay, so in Maple, the problem is there aren't a lot of good programs out there that do vector fields. So let's play around. In Maple, you would do like with plots. That's a package that loads commands. So I'm going to pop over to Maple real quick, and I'll show you the I'll write the syntax down later. So let me see here. Do a share over to Maple. And I've still got this thing loaded here. I don't want that anymore, but I'll do the with plots command. That, and then actually I'm going to show you what's in there. So if you say with plots, it loads these commands. There's a whole bunch of them, but one of them is field plot right there, and another one's field plot 3D. So that is going to be of interest for the three-dimensional ones. So I'm going to just try and guess the syntax: field plot parenthesis. I think a vector in Maple is a square bracket, and the one we just did would be negative y/2, comma, x/2. So that's a vector in Maple. And then you just give a range of values for x and y. Now I went from sort of from -2 to 2 on x and y, but I think I'm going to go from -5. Oops. You have to say x equals -5 dot dot 5 like that in Maple. And same thing for y. Y equals -5 5. I think this will work. Let's see what happens. Yeah, that's a nice field. Kind of a swirling whirlpool. It scales the vectors down because these vectors are supposed to be a lot longer than what you're looking at. And what they do is, because it would be absolutely, the vectors go right, they go over on top of each other if you don't scale them. So it shortens the vectors proportionally so that they don't overlap, but they're all the correct size relative to one another, if that makes sense. Okay, are you telling me this is frozen? You guys seeing this okay? Could somebody just let me know?
Yeah, it's fine.
Okay, thank you so much. Okay, so that's kind of cool. And again, you can pick any range of values you want. I mean, what we just drew was -2 to 2. It'll draw a lot more vectors than you would ever do yourself. But you can see it drew it's just a much more dense field of vectors than you can do. And it always scales them so that they don't overlap. Okay. The 3D field plot, let me just show you a real quick example. So it's field plot 3D. And you just use the same syntax with the square brackets like this. And I'm going to do -y/2, x/2, but I'm going to give the z coordinate something else. So this is, the x and y coordinates are the same as what we just did, but I'm going to give a third coordinate. So I expect this to be swirling in the xy plane. So -y/2 and then x/2. So that's the same. And then I'm just going to take the z coordinate. I kind of want the z coordinates to change. So I want these to point toward the origin. So I'm going to have the z coordinate get divided by 4 just because. Okay. And then you can give ranges. You normally want to do this over some cube or some rectangular prism or whatever. And so I'll have x go from -4 to 4, y from -4 to 4, and z from -4 to 4, like that. Oop. Okay, and so you get a neat three-dimensional thing. And it's funny, it does colors. If you look down on it, it's that same swirling whirlpool. It's hard to make sense of. I almost don't like the different colors that they do. And in Maple, there's always a way to change the colors. I usually just put the command in, comma, color equals like black. And I don't know if that helps me. That definitely does not help. So, you get this. It's sort of like a tornado, though. Okay. And this is an example of a field that's not conservative. Because tornadoes like this spin things around forever. And that's sort of making energy out of nothing. Okay. And if you can make energy out of nothing, that's just not conservative. Conservative fields, if you want to get something out of it, you have to put something into it. So if you want to roll down a hill, you got to climb it first, right? There's this one here, if you just set in this field, you're going to start rolling and you'll never stop. There's no work. It's free. Okay. Any questions? The field will do work on you, but you don't have to work against it to get that free ride. Okay, so that's a non-conservative field. Anytime a field spins like this, anywhere, if there's a spinning nature to a field, those aren't conservative. And we'll see that as we go forward. Okay.
What would make this like a cone?
I don't know. You're asking hard questions. I don't know. Don't ask.
It's Blur's Day, sorry.
Yeah. Okay. All right. So anyway, I'm going to put the syntax in here in case any of you guys is using Maple. And I know none of us can use Maple at school, but at least I wanted you to see a good graph of one of these. So I'm going to go back to my iPad for a minute and just show you the syntax I did. Just keep in mind we're going to be moving around in these spaces where these fields exist, and we're going to be trying to. The first thing we're going to do is try and figure out how much work a field like this would do if you move around in it. You know, moving an object in a field, the field is providing some force, and it will move things. And so, how much energy is expended as it does that? So let me go ahead and give you we're going to be living in these spaces, and it's nice to have a tool. I'll show you some more that don't require Maple. So in Maple, you do with plots, and let's say you did, the first command was field plot, and we did a vector, and we do like negative y over 2 comma x over 2, and I had x go from -2 to 2 and y from -2 to 2, and then Maple likes you to end with a semicolon, but it's not required. Oops, I did not need to do that. So the command technically closes parenthesis, ends with a semicolon. That's a 2-dimensional field. You could type any field you like, but then the 3-dimensional field, we would do field plot 3D. And then just give 3 coordinates. So like I was doing before, -y over 2, x over 2. I think I did -z over 4, just as an example. And then again, ranges for x, y, and z. So x goes from -2 to 2. My bad. Dot, dot, 2. Same thing for y. But now you have to give a range for z also. And you can play around with that. That's a pretty simple field, but it illustrates the point. Okay, this is our 3D field. Okay, so, and then maybe, hang on, let's see what we can do here. I gotta tell you, what's out there is not great, but I'm gonna pop over to my web browser again and show you some of the things I've played around with. GeoGebra does not graph fields, but I have seen people make some pretty cool applets. So like GeoGebra 3D vector field. How about that? Hit enter. Just Google it if you need something. Okay, look at that, vector field 3D. This is not a native GeoGebra file. This is something somebody's programmed in. And this to kind of give you a sense of how versatile GeoGebra is. So here, and I think you can click on that and rotate it. Yeah, so I'm clicking on this field that this person has entered, but he lets you change it, or she, or whoever it is. So my P, see, they're not entering it as a vector. They're doing the P, the Q, and R the way we did in our notes. So I think I had done X. Oh, please tell me I can change this. Okay, the P here was negative X, no, Y over 2. Like that. The Q, I think I did X over 2. And the R, I did negative Z over 4, right? Okay, and I don't know why they reformat this, but this is pretty darn good. Oh, and you can spin it. I just love that. Isn't that gorgeous? Come on, what do you want? So that was Juan Carlos Ponce Campuzano. Okay, thank you, Juan. Super cool, right? So that's if you have to do a 3D field in GeoGebra, I just Googled GeoGebra 3D vector field. It was the first one that came up, and I know there's more because I've played with them. Look at, there's a bunch, and I'm guessing they're all basically the same. There's a different one. Look at that. Isn't that gorgeous? That looks like the inverse of gravity right there. I'm trying to get it to play for me. I don't know how to get that one to work, but oh, there. Woo! Except for it's not rotating. I'm not sure. This one you can't rotate it. You just click on the view button and it changes direction. Still pretty cool. And you can obviously change this. This does look almost like an inverse square. Gravity points to the center of the Earth. So if I put a minus sign in front of each of these components, trying, there we go. Put a minus sign in there. Coronavirus, so you're thinking of vector because of the whole, I get it. So yeah, you're clever. Now, so all I did to this was just make the vectors point into the middle of the Earth the way gravity does, and you can scale them so they're not too long, and that way they don't overlap. And so this is like a gravity field. Okay, and the vectors are super short. If you don't like that, you can make them longer. Yep, super cool. Okay, so like I said, there's as many of these out there as you can ask for. It's not as free form as I'd like, but it'll work in a pinch. So just, like I said, I just Googled GeoGebra 3D vector field, and there's all kinds of people that are solving the problem. The GeoGebra doesn't do it natively, but you can make it do it, obviously. And GeoGebra is an amazing tool for writing programs. So I really recommend it if you have to graph stuff. I've had a lot of fun with GeoGebra. I've had a lot of frustration too. So nothing's perfect, right? Anyway, let's get back to the iPad real quick here. Okay. Just a couple other notes. I have to do inverse square fields, so let's do that. I was showing you a gravitational field a second ago. First of all, this symbol means is proportional to, in case you've not seen it. Okay, so X, alpha, Y, I don't know if that's an alpha or not, but anyway. This means that X is proportional to Y, or X is some constant multiple of Y, okay? If X is inversely proportional to Y, you do this. So that means X is inversely proportional to Y. I don't know why I'm putting this up now. Okay, so that means that X is like K over Y. That's how you do inverse proportions. Okay, So the inverse square fields these would be electric and gravitational fields. And I don't know what else. I mean, I know there are other fields that particles live in quantum mechanics. And like I said, I know that the Higgs particle lives in a Higgs field, but I don't think that's an inverse square field. And again, lots of things have inverse square properties, like light intensity is an inverse square thing. But normally we think of light as a scalar, even though you can think of it as a vector if you're thinking of light as like the velocity vector of a photon. And of course, light intensity diminishes with the inverse of the square of the distance to the light source. So in that sense, the light intensity, or you could do sound intensity as well. These all would be inverse square. But the main fields in physics here with the inverse square is the electrical and gravitational fields. So first of all, F would be the field. And I always use R for a position vector. That's just X, Y, Z. Position vector. Okay. And inverse square fields have the magnitude of the field proportional to the inverse of the square of the magnitude of the position vector. And that's just the magnitude of a position vector is the distance to the origin. Okay. So this is the intensity. Of the field. Okay. The direction of the field this is toward or away from the origin. Okay, so that means we'll have to use a unit vector that's just R over the magnitude of R. So this is just a unit direction vector. Okay. And then again, to say that the field is proportional to 1 over R, I probably should have done the following, that the magnitude of the field is equal to a constant over the magnitude of the radius squared. So that's what this statement of proportionality is. So sorry to squeeze that in later. But fields, as any vectors, have direction and magnitude. So if we combine direction and magnitude, then the field is equal to its magnitude times the unit vector. So the strength and the direction are brought together with that statement. And that's easy enough. So the strength is K over the magnitude of R squared times the unit vector, which is R over the magnitude of R. So it's a weird thing that an inverse square field actually has a cube in the denominator. It's sort of an inverse cube, except for not really, because the R in the numerator sort of kills the magnitude of an R in the denominator. I don't know if that makes any sense. But, I'm going to do magnitude of R to the third down below, like that. So that's the inverse square field. The only other thing I would add is in parentheses, magnitude of R would have to be the square root, because R is XYZ, remember? Magnitude of R would be the square root of X squared plus Y squared plus Z squared. Okay. So the field then being KR over the magnitude of R to the third, you're going to have to bite the bullet and say that's K times X, Y, Z over the square root of X squared plus Y squared plus Z squared. And that's to the third power, yuck. And if you really want to get serious about this, then you might do it this way. Kx over, you're going to have an x squared plus y squared plus z squared, and that's to the 3 halves. Okay, so I'm just distributing the scalars through as a vector multiplication. Okay. And you're going to have this in all 3 components. So this is going to be a little ugly. And I'm going to do a cowardly thing and just copy that part and paste into all 3 components. So you're going to have a ky over the second component. I'll just copy and paste this and change it as needed. So second component, ky, third component, kz. With commas between them. That's an inverse square field. Not fun. For gravity, K is negative. Is negative. Big M, little m, G. Okay. Big M is the mass of a planet or a star. or any object. Every object has gravity, right? Okay, little m, that's the mass of an object in the field. And big G is the universal gravitational constant, just like saying that. And some of you guys even know the value. And I don't. But I'm proud to know you, if you know it. I'm proud to know you either way. You're all beautiful people regardless. Some of you guys know what K is for an electric field. It involves the elementary charges and whatnot. I'll leave that out. You can look into that. They'll throw it at you in the book at some point, I'm sure. Then the last thing here, and I guess we're not gonna get to 16.2 today. So I'll probably just let you off the hook early in a minute. Let's go ahead and do the very last thing. So technically, the gradient of a scalar valued function is a vector field. And this is actually really important. Scalar valued function is a vector field. And so if you have, like, let's say we have P of X, Y, Z is equal to let's do K, maybe a negative K over the square root of X squared plus Y squared plus Z squared. Okay. That's horrible. Oops. And maybe if you felt like it, you could say this is negative K times X squared plus Y squared plus Z squared to the 1/2. Negative 1/2, my bad. Okay. So then let's do Px. This will be the derivative with respect to x. So I think you're going to get a negative k times a negative 1/2 times the derivative. I'm going to put the derivative in. Well, I'll do that last. So we'll have the x squared plus y squared plus z squared to the negative 3/2. Oops. Right? Okay, and then you have to multiply by the derivative of what's inside, so you're going to have a 2x in there. Now tell me if I'm wrong. Is this, the negatives cancel, the 2's cancel, so I think this is kx over x squared plus y squared plus z squared to the 3/2. You guys got that? What do you think? Yeah? Okay, thanks, Travis. px, and then just by symmetry, I think py is going to be ky over x squared plus y squared plus z squared for the 3 halves. And again, by symmetry, pz is going to be kz over x squared plus y squared plus z squared to the 3 halves. So it turns out, actually, the gradient of p is, well, it's the thing. Can I just copy it from up above? So, I mean, obviously, it's a vector with components px, py. And remember, this is also called the total derivative again. Px, py, pz. Okay? But that's this dude up here for the inverse square field. Okay. So it's just weird. This, just turns out that this is the inverse square field. And then I just wanted to throw out a little trivia. Trivia. A fact that nobody cares about. Turns out to be consequential. So it turns out that the gradient of P is equal to the inverse square field. And if a vector field has a function whose gradient is the field, then the function is called a potential function. So if big F is a vector field, and there exists a scalar function, little f of xyz, say, such that the gradient of little f is big F. Of course, this is little fx, little fy, little fz. And let's say, and that's a vector field. If it turns out to be equal to big F, then big F is called conservative. Okay, so this is actually a list. Then let me move these down so it's for the list. Okay. Bullet points. Big F is conservative. Little f is the potential function for big F. Why is it called potential? If big F represents a force, Now think like a gravitational force or an electric force between two particles. Okay. Then the negative of little f of xyz is potential energy. What? Okay, that's just trivia. I don't have time to prove that right now. So I'll just zoom out on this here. I'm done talking. If you want to type a question, I'll answer. If you want to verbalize a question, I'll answer. I'm just going to sit here for a moment or two until I get sick of it. And that's it for the night. And be watching your, please be watching your emails.